Hi, we are Mercer University Team 1068, and we used an epidemiological approach to model Twitter moderation methods. My name is Chirayu Salgarkar.
I'm Brody Dutka.
I'm Sahan Vangala. All right, problem statement. The objective of this project is to measure the role of different moderation methods and their spread of misinformation. So the first case of a moderation method used on Twitter would be censorship of whole posts. This is where you completely block an individual from accessing possible misinformation. And the second case would be warning notices on posts. This is where you give an individual a choice to access certain misinformation. The implications are that it's likely that interaction coefficients change for cases of both censorship and warning notices. For cases of warning notices, spread might be confined to those ignoring notices, while for censorship, there's less ability for consumer input. Our assumptions are that the source of misinformation is from a single individual to their followers. When time equals 0, an initial individual makes a post of misinformation, which is now available to their followers. A single individual has the potential to spread misinformation to their entire following group. Not every individual who receives misinformation believes that misinformation. Likewise, not every individual who believes the misinformation acts in spreading the misinformation. The more interactions an individual has with misinformation, the more likely the individual is going to believe it is true. The size of Twitter is a large population. However, individual follower counts may not be that large.
This leads itself to an epidemiological model, funnily enough. We imagine misinformation posts represented almost as like a pathogen with the potential to spread through a population. This leads itself quite effectively to compartmental models. Compartmental models allow us to represent individuals with closed populations that belong to mutually exclusive groups, i.e. infected, not infected. They can also represent groups found in Twitter followings, those who have accessed or seen the post, those who have not seen the post, those that believe the misinformation within the post, those that don't believe the misinformation within the post. And because of that, most compartmental models are directly related to epidemiological modeling, one example being the Kermack-McKendrick model. The Kermack-McKendrick model consists of 3 coupled nonlinear ordinary differential equations, SIR. S stands for susceptible, whether or not they're susceptible to a pathogen that is passing through a population. I being they're infected, they have been contracted with the population, and R being they've recovered. They contracted the illness and they have recovered from the illness. This works very well for models such as the flu or Ebola, where there's a population that is susceptible, there's a population that is infected, and there's a population that is recovered that does not go back into the susceptible or infected population. However, for this case, we found that the model often oversimplifies the problem. And for that, we adapted the SIR model. The SIR model has some specific assumptions that the change in population with respect to time is 0, and population is going to be susceptible plus infected plus recovered. However, in the case of Twitter, those who are infected are not necessarily spreaders. So what we decided to do was split the infected population, I, into 2 groups. Those who are likely to share content and believe the content, and those who believe the content but are not necessarily likely to share the content. We operated under the assumption that act of being infected per se is believing the misinformation withheld, not necessarily sharing it or not sharing it per se. So we separated the 2 components into I non-spreader and I spreader. We also did not take into account individuals who have been exposed but not get affected, i.e. people who see the post but do not believe the post. We can include this by adding another component, E for exposed, which creates an SEIR model, which exists, but our model also includes a separate sections for non-spreader and spreader. One example of an SEIR model is shown above. Incredible thanks to Drs. Peng, Yang, and Zhang, among others, for developing this model. They used a generalized SEIR model for COVID-19 outbreaks, and they have separated them into susceptible, exposed, infected, quarantined, which means that they're separated from the population, another good use of a compartmental model, into recovered and those who passed away. We modified this slightly, And we set it to that S of T, or susceptible of T, are those who are susceptible to Twitter misinformation. E of T are those who are exposed to Twitter misinformation, i.e. they see the tweet on their feed, or they have been able to access that tweet. I spreader is those who are infected and choose to spread it, i.e. by liking a post or by liking a post. And non-spreader would be those who believe the misinformation but do not share it. This means that any sort of moderation method would be occurring between the susceptible and the exposed population, because any sort of moderation method, whether that be blocking the post from even being accessed or adding a warning, changes whether or not those in the susceptible population are exposed to the tweet at hand. R of T, or the recovered, are those who move from believing to non-believing the misinformation. They have agreed with the misinformation previously, and they've moved to the non-believing case. We would expect this to be a much smaller percentage, and much higher portion of people would stay in I, because generally, at least as seen in modern times, there's a much stronger case for those staying in the infected population and those moving into the recovered population. This means that we can model this as a system of differential equations. We found it easy to first start off by looking at the recovered population and then moving up onward. The recovered population would be equal to the sum of the infected population with respect to time of the asymptomatic group times a gamma function, which is an arbitrary parameter for the percent, or like the proportion of people who are infected and asymptomatic, i.e. don't share, and now end up not believing the material. That's going to be added to the infected symptomatic population, multiplied by a separate parameter, gamma 2, for those who previously believed but do not believe anymore. Then dIdt, or the proportion, the derivative of infected with respect to time, would be negative drdt, because it's going to be the opposite direction of from I to R, plus the exposed population times alpha 1, plus the exposed population times alpha 2, A2, sorry. So that is just going to be the sum of the infected populations that are going to be coming in. That's going to be exposed times a constant, so a proportion of those exposed actually end up getting infected, and a proportion of those exposed actually get infected. So we separated the infected parts into two components, and the way we separated them is by having a certain proportion of the exposed population that is infected actually get multiplied by a specific constant, and a certain proportion getting multiplied by a separate constant. Then similarly, dEdt is going to be the negative of E of T times alpha, which is A1 plus A2, plus the susceptible times the symptomatic infected population that ends up exposing another population to the virus, times a coefficient beta, which is the interactivity coefficient, i.e. how often will a person who gets shared will be able to share the material to another group. Therefore, any sort of blocking mechanism would actually be changing beta, and not necessarily any of the other variables. Similarly, dSdt is going to be 1 minus S of T times the infected population symptomatic times that beta, or the interactivity coefficient. With some initial conditions, the initial susceptible population is going to be S naught, the exposed population is E naught, I naught, and R naught. S sub 0 is assumed to be a positive real number in this case, because you're going to need a specific population.
So in order to get results from our model, we decided to use the numerical method of a fourth order Runge-Kutta. So we decided to use Fortran, and here's the code for it. The first picture is the main driver of the program. It's calling all of the differential equations and adding them to our populations to get the change in through time. And then the second picture, you see the X prime function. And this subroutine is going to give you back all your differential equation values. So that's where we derived our results from. And then next, so this model is with a beta of 1. So that means that's Twitter with no moderation techniques. And here you see the exposed rate just jumps through the roof. And that's because as time goes on, more people are exposed, and that number just keeps going up. And then in here, we see following that are the infection rates, which would be lower than your exposed. And then under here, you see the there's not many people recovered, because once they start believing in it, they're pretty hard on their thoughts. And then as well, you'll see the susceptible population near zero, because they've all become infected through all the iterations. For our next one, of beta of 0.5, we're treating this as the case of strong content warnings. It's not stopping everything that's going through, but it's limiting the amount of people who are having access to the content. And here you see the range has been shortened, because now that it takes more time for the interactions to first happen. And then you'll see here, you see the same trend in the slopes of all the variables, but it starts off a little bit slower because there's more restriction to the interaction. And then lastly, we have a beta of 0.25. This is to represent the complete moderation of misinformation, where they stop the post before it's even been posted. We decided not to make it 0 because we're taking into account the misinformation that isn't being picked up by the algorithm, which still slips through the cracks through encoding. But as you see, the infection rate is a lot less, and the exposed rate is a lot less, because just significantly fewer people are seeing it.
Yeah, our model does not account for groupthink. As our system is perfectly mixed, we don't have clusters of people who have similar thoughts and beliefs in this setup, because we have an arbitrarily large population for Twitter. Therefore, this shows relatively curved data, while actually we would see more spikes within the data where a certain group is more likely to spread misinformation. That increases the population, and then leads to a smaller population in other spots. Another thing that we did not account for is likes versus retweets. We only account for the idea that sharing misinformation directly means you agree with it. That's not necessarily true. You can quote on Twitter, and you can share material that does not necessarily mean you agree with it. Variables other than beta were arbitrarily given, and we would actually need to know more Twitter data analysis for actual values, and that would require extra time. Our final conclusions: Twitter misinformation spread can be modeled somewhat effectively as a compartmentalized disease spread model. The ability to handle misinformation spread in our model is based on a solitary variable, beta, which has a direct impact on interactivity coefficient. As beta approaches 0, there is more regulation on the spread. With minimal regulation, misinformation spread is seen to be exponential. As beta decreases, the ability to handle misinformation is more controlled. Our model is limited in depth, but relatively applicable to future scenarios, as significant variables are given, but not analyzed numerically, such as alpha and gamma. These are our references. Thank you so much.